In this video, we look at proving the proportional division theorem, which states that a line drawn parallel to one side of a triangle divides the other two sides proportionally. Before we get into the proof, there is a key concept that we need to explore. Now, let's consider this pre-drawn situation whereby the line AD is parallel to the line BC. You can see that there are two triangles, ABC and BDC, and these two triangles lie between these two parallel lines AD and BC. Now the area of triangle ABC is going to be, with BC as the base, is going to be, if I drop a perpendicular here, the area of ABC is going to be equal to a half times the base, which I'm calling BC, multiplied by the perpendicular height, which I'm going to call H. And so that gives us the area of ABC. Similarly, I could find the area of triangle BDC, and that area, okay, I'm looking at the triangles, is going to be equal to a half of the base BC times by the perpendicular height. And you can see that the area of these two triangles are equal, so therefore A of ABC equals the area of triangle DBC. So this is actually true all the time. If two triangles lie between two parallel lines and they share the same base, they will have the same height, and therefore the areas are going to be equal. Let us now suppose that we have a new triangle which is drawn here, and this triangle, let's call it triangle ABC. Now what the theorem says, if a line is drawn parallel to one side of the triangle, divides the other two sides proportionally. So if I'm going to draw a rough drawing here and say that this line which I've just drawn, let me call it DE, is parallel to the third side, it is going to divide these two sides, AB and AC, proportionally. So what we want to prove is that the ratio of A to D divided by B to D is going to be equal to the ratio of A to E divided by C to E. Right, so that's what we want to prove. Now I'm going to draw a perpendicular from the point E to the base A. So let's suppose that we've got a perpendicular like that. I'm going to call that perpendicular H, the height of the triangle ADE. Now if I were to then work out the area of triangle ADE, if you allow me, I'm going to write it as A of ADE. It's going to be equal to a half the base, and you can see the base is going to be AD, that's where the height makes the perpendicular, AD multiplied by the height, which is H. I'm going to work out a ratio of this triangle with triangle CEBD. So if I were to complete this here, alright, if I were to do that, I'm creating a new triangle, triangle BDE. You can see that. Now, triangle BDE and triangle ADE share the same vertex angle, the vertex E. So it follows that the highest point of triangle ADE is going to be the same as the highest point of triangle EDB. So therefore, if I were to drop a perpendicular again, the perpendicular, maybe this drawing is a little bit misleading, so my height could look something like that to make a 90. So that is going to be 90 degrees there. So the highest point of triangle ADE is the same as the highest point of triangle EDB. Okay, so then the area of BDE, triangle BDE, is also going to be equal to 1 over 2 multiplied by the base. The base this time is going to be BD multiplied by the height. So I'm creating a ratio of those two areas. Okay, so now this is going to cancel out with that, and this also cancels out because the height is the same. So this is H here, and I'm left with AD divided by BD. you can see I've already found the first part of my proof. I now need to show that this is going to be true again for AE over CE. Okay, to find the area of triangle ADE can also be done in a different way. If I were to draw a perpendicular line to this opposite side, the base of this triangle then becomes AE, and the height is going to be equal to K units. So if I write here the area of triangle, the same triangle ADE, which we calculated just now, is now going to be given by a half multiplied by the base, the perpendicular is AE, times by the height, which is now equal to K units. I'm going to divide this by the area of a new triangle which I'm going to draw through here all the way to C. So it's now EDC. Can you see that triangle there if I made a solid line? Okay, so the triangle is this one here, ACDE. Now, using the same argument as previously, you will find that the two triangles share this vertex D, and the highest point of triangle ADE is the same as the highest point of triangle CDE. So if we drop the perpendicular, their heights are going to be equal again. So the area of triangle CDE is going to be equal to a half multiplied by the base. Now the base of triangle CDE is equal to CE times by CE multiplied by K. As before, these two constants are going to cancel out, so I'm left with AE over CE. We are almost there. Remember, at the beginning of the video, I told you that it is important for us to prove that if we have two triangles between two parallel lines, then their areas are going to be equal to each other. So you can see that the triangle BEC and triangle CDB recreates this situation here that we started with. So it follows that the area A of triangle DEC is equal to the area of triangle BEC. So these two, based on this proof that we showed earlier. Now it's downhill from there. If I make a bit more space here, it follows that the quotient A of ADE, so therefore A of ADE divided by, so the triangle ADE divided by this one here, the area of triangle BDE, is going to be equal to the area of triangle ADE, this one here, divided by the area of triangle CDE. I hope you understand that if this area is constant in the numerator and these two denominators are the same, then the quotient is constant. Those two are going to be equal to each other. But you and I have shown that this left hand side is simply equal to AD over BD. So therefore it follows that the left hand side is AD divided by BD, which is going to be equal to the right hand side, which is A of ADE divided by A of CDE. So that's that one there. So A over AE over CE. And that is the proof of the proportional division theorem.